section is about limits and continuity. But we did do limits and continuity. But that was for vector-valued functions. This is now going to be a little different. In 2 dimensions, so what you guys are used to dealing with, if you have a function f of x, and we have a point at x naught, y naught, one intuitive way of knowing whether the limit at a point exists is to say that if the limit as x approaches this x value, x naught, from the right of f of x, if that equals the limit as x approaches that same x value from the left, that's one way to argue that this limit is there and that it exists. You guys remember talking about that, right? Like sometimes there might be a hole in the graph, but you're like, well, no matter which way we come from, if we come from the right or the left, we're still getting really close to 3, let's say. So we'd say that the limit would be 3 at that point. Well, in 3 dimensions, let's start by drawing a surface. So here's our f of xy, or at least a portion of it. And let's say I'm interested in the limit as, well, now it's a little different because in 2 dimensions we had one independent variable. So we would say as x approaches a value, right? Here we have 2 dependent variables, so we'd actually look at something like the limit as xy approaches, x naught, y naught of f of xy. So this is what we're talking about. We want to know what this is. So visually, let's say right here is x naught. Let's say right here is y naught. I would go to the point x naught, y naught, which is right here. And then I would try to figure out if there's a value there or if we're approaching that value from every direction. The problem is, how many directions can we approach this point from? Infinite directions. We could approach it from, as we come parallel to the x-axis, coming from behind, going forward. We can go the y-axis, from the left, from the right. We can go at different angles. We can go along different curves. So the issue becomes, there are infinitely many paths or let's say curves that can approach the point x naught, y naught, z naught. So we could get there by following this path. We could get there by going this way, going that way, and so on and so forth. So now this notion of what we did in 2 dimensions, like, well, if we approach the value from one side and the other side and it's good, then we're good. Not so good in 3 dimensions anymore. Because you'd have to say, well, no matter which direction I approach from, it's the same value, which is a bit cumbersome because there's too many directions to look at. Okay? Let's take a look at this in action. Let's say we have f of xy equal to negative xy over x squared plus y squared. And let's just see if we can find some limits along specific directions first. So let's find the limit along the x-axis. What's the equation of the x-axis?
Y equals something.
Okay, y equals 0. So then this is what we're talking about. We're saying, let's look at the limit as x comma y. And let's say we're approaching 0, 0 of the function that we're looking at. We want to figure that out. Okay, when we have a specific direction, figuring out the limits is pretty straightforward. If we know that y is equal to 0, then this translates to the limit as x approaches 0 only, because y is 0. So if I were to plug 0 into the original function, now what's the function that's left over?
0 over x squared.
Okay. And this is the same as the limit as x approaches 0 of 0. So the limit is 0. Okay, any questions on how we're doing that? So if we're given a specific direction, we know y is 0. We can go ahead and plug 0 into the y's, take a look at how that changes the function, and then reevaluate this limit now as a one variable limit. I saw a hand. Or you got it? Okay, yep.
Why do we do that? Because if we plug in 0 straight in, it could be 0 over 0. We can't.
But we're not plugging 0 straight in. We're only plugging in 0 is equal to y. So what we're saying here is that we're approaching this function along the x-axis.
Yeah, no, I understand that. Limit x to 0 of 0 over x squared. I know that equals 0, but...
Oh, well, I think I know what you're saying. This is not the answer to the question, what is the limit as x approaches 0 and y approaches 0 of the original function?
Okay.
This is just the limit as we approach it from one direction. So we haven't exactly found the limit yet. Okay? Actually, let's look at what happens if we go along the y-axis. What's the equation of the y-axis? X equals 0, so let's evaluate it just to see what happens. So we're looking at the limit as x and y approach 0, 0 of f of xy. And if we're going along the y-axis, then x is equal to 0, so I get 0 on top again, over, oh, sorry, messed up my notation. This is now the limit as what approaches? Y approaches 0 of what? 0 over y squared, which again is pretty much what we had before. Okay, so all we've done so far is said, well, look, from this direction the limit's 0. From this other direction the limit is 0. Yes?
Did you show that on the picture? The going along the x and y axis?
Yes. I can't do that because I'm recording the lesson.
Oh, absolutely.
So after I'm done, I'll pull up the function because I have it on Maple. I just can't do it now. But, and I cannot craft this by hand. You'll see why when I put it up there. Okay. Let's do one more, just for good measure. What about if I approach it not along an axis, but along a curve, or along a different equation, like y equals x? So if we start with the limit as x and y approach 0, 0 of f of x, y. Again, here's our original function. If y is equal to x, just pick one to stick with. So let's say I'm going to stick with x. So x approaches 0. So now everywhere there is an x, or I'm sorry, everywhere there's a y, you're going to replace that with x. Does that make sense? So the numerator becomes negative x squared over 2x squared, which is the same as the limit of negative 1/2 as x approaches 0, but that's just negative 1/2. So what have we done? We played around with different directions. Twice we got the same answer, but then this other time we got a different value. Okay? This is not very helpful, right? The point I'm trying to make here is that this is a bit cumbersome. It helps you see what's going on as you approach a function from different directions, okay, but not the most useful. Here's the formal definition.
So would that mean there's no limit if we got different limits?
Yeah. This is essentially going to become a way of proving that there isn't, or that the limit does not exist. Okay. And we'll make that clearer in a minute.
Wait, so that's all wrong?
No, this is not all wrong. This is all correct.
Just don't do that.
Okay.
All this means, the answer is that the limit doesn't exist. We haven't clarified that yet.
Okay, thanks. Just trying to get to the answer.
No, but the last one was negative.
Yeah, but the next
All it takes to show that a limit doesn't exist, which again I'll clarify in a minute, is for you to find one path where the limit is different than other ones. You could get there 99 different paths and get 0 if you wanted to, and if you find one path where it's not 0 and maybe it's 2, or in this case negative 1/2, the limit doesn't exist.
So I have to do it on these times.
Well, we're not going to do that. Yeah. Okay, so here's the formal definition. Let f be a function of two variables and assume f is defined at all points of some open disk centered at x naught, y naught. So what we're saying so far in the definition is, here's this disk, and we're arguing that the function is defined everywhere within this disk. Okay, this is the analog of the limit definition that you learned in Calc 1. Okay, in Calc 1, you had an interval, right? You had an x-coordinate, and then you went out a little bit to the right, and you went out a little bit to the left, right? And we said, let's say that we're good here. What does this limit thing mean? Now we're looking at 3 dimensions, so instead of going just left and right, we're going out a certain radius. Okay? And the only thing that we could maybe have is maybe it's not defined, except maybe at the actual center. We don't need the function to be defined at the point in order to have a limit there. Okay? But it should be defined everywhere else so that we can see what's going on. Then what we say is this. Then the limit as x, y approaches x naught, y naught of f of x, y is equal to L if given a little epsilon greater than 0, we can find a delta greater than 0. Why are we giggling?
That is not the delta sign. What is that? The different delta sign?
Yes.
No, it's like,
Is that like a lowercase?
I forget which one's which, but that's also...
He's referring to the triangle.
Yeah, you're thinking of the triangle.
I can't write the triangle. Is there something else? Is
It-
there different delta?
Did you guys learn the formal definition of a limit?
No.
They removed the part.
They removed it? What do you mean they removed it? Like you don't need to know it for calc?
Absolutely not.
No,
Absolutely.
Never use it.
Well, that makes things interesting. Okay.
What is that sign?
It's an upside down row.
Isn't that epsilon?
This is a little epsilon.
Yeah. Isn't it?
This is a delta, a different version of it. I forget which one's which. I think this might be lowercase. The other one's capital delta. Such that the difference between f of xy minus L is less than epsilon. Yes.
No, it's not a Greek sign. Actually,
Whenever the distance between xy and x naught y naught satisfies the inequality, 0 is less than the square root of x minus x naught squared plus y minus y naught squared less than delta. In Calc 1, everything is the same except it would say let f be a function of one variable and assume f is defined at all points except maybe at x naught. Then we say that the limit of f of x as x approaches x naught is equal to L, and everything is the same. Given some little epsilon, we can find a delta greater than 0 such that the difference in these values is less than epsilon, and then we say whenever the distance between x naught and x satisfies 0 less than absolute value of x minus x naught. So it's just this part, essentially, because we only have one variable. Okay? Essentially, okay, this conveys the idea that the value of f of xy can be made sufficiently close to L by picking correct x and y values. So all this is saying is that this limit here is going to equal some limiting value L as long as, if we're really close to this point, everywhere we plug in values, we get L, or something really close to L. That's all that means, which is the intuitive definition of what we did up here. Right? When you plugged in a point really close to x naught from the right and a point really close to x naught from the left, what should you have gotten?
Really
A point really close to x naught from both directions, right? This is just a formal way of saying that that needs to work from every direction. Okay? This is just more formal than what I just said. If you're worried about this being on an exam, don't worry about it. Okay? But you should know the notion that we just went over intuitively. Does that make sense? Yes?
So how does this help us?
We're getting there. As far as helping you evaluate limits, it's not really going to help you too much. But I just want you guys to understand what the definition of a limit is in three dimensions. Yes?
What is epsilon?
It's just an arbitrary constant. Hold on. Let me see if I can remember my Calc 1. Where's that? So, back here, this was x naught plus epsilon, and this was x naught minus epsilon. And then usually what we argued was that we can get really close to the y naught value. So this would be like y naught plus delta, y naught minus delta.
Okay.
I'm sure you guys did this.
This is a pre
No.
Not in count.
Pre-calc. Yes, Mrs. Weber had taught you this.
I don't.
Wait for it.
Warning.
So we did exactly the Nazis does this.
Guys, let's line
Okay, guys.
Hey.
Before she comes, do you remember how every single day she'd be like, oh, I forgot to tell the other period this? Bring that up. She always messed up the other class's notes, yeah. Then she realized it when they gave more class. No.
So here's your pre-calc teacher.
Mrs. Weber.
Wasn't my
Does this idea of a limit look at all familiar? With epsilons and deltas and talking about...
It's even video. Remember I taught it, but then a lot of people are confused, so I put this video on there.
Please
So I can show you. I can bring the video up right now.
Okay, Mr.
Do
Whitman.
it.
Mr. Whitman.
Okay, so Wheeling students, except for Eddie, have seen this before.
I
But,
totally
okay.
remember it. It's in your calc packet. Did you keep your calc packet?
Which period did you teach it to?
Every single one of them. I did. I remember this.
Okay.
J-Trom's the only one that shouldn't remember because he was like asleep.
He's the one with those.
Oh, didn't you remember?
Okay, anyway,
Great fun.
thanks.
Yeah.
All we're doing is taking this, which obviously makes no sense to you if you never saw this before, but extending this notion to 3 dimensions. You know what? Let's just go forward. There's no way. This would take like 3 days probably to really dissect.
No, it kind of makes sense. It's just like-
I mean, it intuitively, yes.
Yeah.
The hard part of using this definition is actually, if you're given an epsilon, finding the appropriate delta, and that was annoying if you did it in pre-calc. I remember doing that years ago. It was not very fun.
Essentially, I did not understand.
Wait, but do we have to do that?
No, you don't have to do that.
Okay.
All I want you to know is that the definition is the same in 3 dimensions, except the only difference is instead of saying, look, if I give you a little epsilon here, you can get pretty darn close to this y0 value within a difference of delta, right? That's all it means. In 3 dimensions, it's not a linear relationship. It's now, here's a center. I can go out a little bit from that. And if I were to plug in these values centered around x0, y0, you would get pretty darn close to z in this case instead of y0. Does that make sense?
Yeah.
That's all you need. That's all you need to know.
So, is
Oh.
delta like a sphere or something like for z, like the values that you could get when you plug in?
Not necessarily. It would just be differing heights.
So that sphere would, or that circle would project up onto the
Yes.
surface?
So now you'd be up here somewhere, and we're saying that on this little curvy circle,
That makes sense.
that this value, the height of the circle, anywhere away from the center, should be pretty darn close to the actual value of x0, y0.
Gotcha.
Okay? All right. Here's what you guys need to know.
This was all just like.
Maybe next year I just won't do that part.
Let's recommend this.
We're getting there. Don't worry.
Just more confused.
This is a theorem in 13.2. It says the following. If f of x, y, so we're kind of recapping what we just said, okay? But making it more formal on paper. This is what you should focus on. If f of x, y approaches L as x, y approaches x0, y0, then the argument is that f of x, y should approach L as x, y approaches x0, y0 along, this is the key, any smooth curve. That's all we're saying. That no matter which way we come from, we should be able to get pretty darn close to the actual limit of L if it exists. If it doesn't exist, then there's going to be one or more directions that we may come from where the limit is going to be different. Okay? B. This is the part we need to focus on. If the limit of xy approaches a point x naught, y naught of a function f of xy does not exist along some smooth curve, or if f of xy has different values along different curves. Hey.
I got a bit of a problem. I gotta take a kid for a few minutes.
Okay.
Wait now.
Yeah.
Can I wait?
If you want your national merit sent in, you better do
No,
now.
I was gonna see what one class I did. I finished everything. You didn't finish your stuff.
It's getting really complicated.
Yeah, you realize how-
We're missing these notes.
Worst case scenario, I'll bring it down.
Okay. Now that Eddie's gone, on the next test. No, I'm just kidding.
Can you move it down a little bit? I didn't get the last.
Oh, sorry. Yeah.
Thank you.
Okay.
Wait, for the top one for A, like, why did you write the same thing twice?
Well, it's not the same thing.
It looks
Okay. If f of xy approaches L as x and y approach a certain point, then f of xy should approach L no matter which direction we come from. That's what this is saying.
It says exactly the same thing.
Now it says exactly the same thing.
Oh, take your hand off, please.
Now it's a little different.
What's L?
The limit. Man, you guys are
I thought I was still waiting.
long day. You've been in school for like 20 or half hour. If you're J-Rum, you've only been in school for like 15 minutes. Okay. The second part. This is just conveying what we did earlier, that if you find a path where the limit does not exist, then the whole limit doesn't exist, no matter what. It also doesn't exist if you find different paths that have different values as the answers. Like we did for the first one, we had 0, 0, and negative a half. So that shows that the first example, in example 1,
Do you just guess the values, or is there some way?
essentially, yes.
So what if you
An example,
fucking all, like-
limit does not exist. So here's what's going to happen, all right? I know you guys are worried. If I give you a limit question, okay, if you can plug in the values directly, you're good to go. Okay? If you can't plug them in directly, then it's either not going to exist, in which case you need to find some paths that show that, kind of like what we did with the first example, because you can't just say this doesn't exist because it looks like it doesn't. You have to actually prove, well, look, here it's a half, here it's 2, different values, doesn't exist. Okay? Or if it's something with discontinuities, there's one other option which we'll talk about. Okay?
Wait, so you're gonna. Never mind.
Okay. Here's an example. Here's what I mean. Let's say the limit of xy approaches, we want to find the limit as x and y both approach 1 and 2 of the function 5x squared y over x squared plus y squared. So if you're approaching these problems from 13.2 in the homework or the exam, your method should be, can I plug in 1 and 2? Yes. What do I get?
10 over 5, 2.
Moving on. That's it. Next example. That's it. Let's say we have something like this. The limit is x and y both approach 0 of x squared minus y squared over x squared plus y squared, all squared. Okay? So ideally we would try to maybe simplify, factor, those same tricks that we did in Calc 1. You can't really do anything with this denominator. Okay? So what I would do is pretty much say, okay, first of all, I haven't shown you the other trick that you can do yet. So right now we're going to go with this probably doesn't exist. So here's how we show that. Let's check along x equals 0. What is the limit along x equals 0? Let's see. So now we just have the limit as y approaches 0 of, if x is 0, then what's left in the numerator? Negative y squared. If x is 0, the denominator is just y squared, and this is all squared. So this is the limit as y approaches 0 of 1, which is 1. Okay? If we're convinced or have a pretty good feeling that this is going to be a weird limit and probably doesn't exist, then we try a different direction and get a different value. So let's say, and I mean you can kind of see, if you plug in x, it's going to be the same story, right? X equals 0. Or I'm sorry, if we plug in y equals 0, right? You have the same exact thing. So why not try along y equals x again? So let's just leave, we'll stick with y. Let's leave y in there. If I plug in y is equal to x, or x equals y, the numerator becomes what? 0. And now my denominator, I get 2y squared, which is the same as the limit as y approaches 0 of 0, which is 0. So what did we just show? We showed that the limit does not exist because these are different values along different paths. Okay?
So how do we prove that it does exist?
Essentially, you have to be able to calculate it.
So like in the first
So, like in the first example, there's one more part that I'll show you tomorrow where you can kind of bring in some polar coordinates to maybe help, and that'd be the other option.
So there is a way that something is formatted like the second one?
Might actually, yes,
Okay.
but it'd have to work out nicely in polar. And we'll do that. We'll finish that up tomorrow.